You might be looking at this subtitle with two different thoughts in your head. Number one, easy. Yes, I like the sound of that. Two, 10 does not sound easy. The good news is it's not 10. The other good news is once we master this kind of nomenclature, all the other nomenclatures that we do are going to be versions of it. So we never really have to do a complete changeover of our way of thinking. So let's focus on this, get it down, because 10 does sound like an awful lot. Even 8 sounds like an awful lot. But once you get it, it rolls into the other ones quite readily. So the first thing that we're going to have is we're going to have a long structure, and we have to figure out the longest continuous carbon chain. And longest continuous carbon chain means if I draw from carbon to carbon to carbon to carbon to carbon without doubling back and without lifting my pen or pencil. Okay? That is going to give us the root name. Now the root names are here. I am not going to read them all through, but what I do want to tell you to do is you need to know these, so you should pause the video and get this down. The other thing I'm going to tell you is that I've got them colored that way because in each one of these root names there's two parts. There is the blue part, which represents a carbon count. That is going to be consistent throughout this unit. Anytime we see 5 carbons, you're going to see pent. Anytime you see 9 carbons, you're going to see let's go with 6. Anytime you see 6 carbons, you're going to have it's going to be a hex. And then there's also the orange part, peach, whatever color that is, that represents a functional group. So all of these end in ane because we're talking about alkanes. If we were talking about different functional groups, then we're going to have different endings, at least in a lot of the cases. Okay, but there is a carbon count and there is a functional group portion to the name. I want you to pause here. I want you to figure out what the longest continuous carbon chain is so that you can tell me what the root name for this one is. I'll wait. Okay, so hopefully you've done that, and we're going to take this up. So in the first one, you should have had 7 carbons as your longest continuous carbon chain for a heptane. In the green one, that's also a heptane. And if you disagree, I'm going to ask you not to look at the straightest chain, but the longest chain. Now, I'm not going to go out of my way to trick you ever, but you do have to be looking for the longest continuous carbon chain, and it won't necessarily be the one that is, let's say, the more obvious looking. You got to pay attention. And then the last one, that should be 9 carbons on the longest chain for a nonane. Okay. Second rule is that we're going to number the chain to give the lowest overall numbers. And what that means is I'm going to count the carbons, 1, 2, 3, 4, 5, from either the left or the right so that those branches get position numbers. So if I take this one, and I numbered it from the left, then from the left I've got other branches at carbon number 2, carbon number 4, and carbon number 5. If I numbered it from the right, however, I would get exactly the same groups, but now the numbers would be different because they are sitting at the 2nd carbon, 3rd carbon, and the 5th carbon. Well, hopefully you agree that from the right gives me lower numbers overall, at least in one spot, but that's all that I need. So I would actually number this one from the right. And it doesn't really matter how it's drawn. I always look to see how can I get the lowest numbers. Now that is one of the rules that we're going to have to tweak a little bit later on, but what we're going to do is end up with a hierarchy rather than just changing the rule altogether. Okay, how about this one? You should pause it and take a look at yourself and make a prediction for you. But for me, if I count this thing from left to right, I have groups sitting at carbon number 2, another group at carbon number 2, carbon number 4, and carbon number 6. If I number it from the right, hopefully I said left last time, but if I number it from the right, I would have my groups at carbon number 2, 4, 6, and another one at 6. The top one from the left, and I'm going to say it again if I goofed it last time, from the left is 2, 2, 4, 6. That is a smaller set of numbers than the other one. This one would be numbered from the left. And again, it doesn't matter how it's drawn. You always look to see which gives me the lowest overall numbers. Okay, pause it. You don't have to draw these out if you don't want to. I think you should. Good practice. But pause it, count them up, figure out where direction we're going to number these from. We'll come back in a second. Okay, time to take it up. This one, the orange one, you should be numbering from the left because I've got better numbers from, or smaller overall numbers from the left. Second one, I'm going to number it from the right, right to left, and then the last one is also right to left. Now at this point I want to throw up a caution flag, because you might be just sort of glancing at this and saying, okay, this end looks a little bit busier, this end looks like it has more stuff, so that's the end. Kind of works, but the problem is, remember, this is one of the rules we're going to have to tweak, because we're going to end up with a hierarchy, so make sure you're actually looking. Third thing is we're going to give those side chains, those groups attached to the main chain, a position number and a name. Now we already know about the position numbers because that was step number 2, but names now. So the top zigzag line represents the root chain, and then I've got these groups attached to it. Now I don't have that many groups, and there's something similar about these groups, then I'm going to talk about them in something specific. If I've got a 1 carbon group attached to the chain, that's going to be called a methyl. Again, I've got a carbon count part to the name, and then it's not really a functional group part. The YL part, the methyl part, tells me it's a group attached to a chain. If it's 2 carbons, it's going to be ethyl. If it's 3 carbons, it depends, because the very first one to the left there, that 3 carbon group is attached to the end. It's dangling all the way down. But I could also have a 3 carbon group that's attached to the middle carbon, and that would give me something slightly different, and that is called an isopropyl. You could probably guess why. By the way, isopropyl is going to be a much more common group for you to see, because you'll notice with the 3 carbons in a row, the propyl group, I actually need a pretty long chain before that group becomes part of the longest continuous carbon chain. We are going to add more later. This is about it for the carbon groups. There's not really much more I can do with that, because again, adding a longer carbon group usually will adjust where the longest continuous carbon chain is. Eventually we're going to put those groups in alphabetical order, so ethyl groups will come before methyl groups, but that's a later rule. Then we're going to identify the side chains. Okay, so on here I want you to again pause it, get an idea for what the chains are. I'm going to throw numbers on these as well, but give it a pause, give it a look, and come back in a second. So on this one, in the orange one, at carbon number 3, I've got a 2 carbon group, so that's a 3 ethyl. At carbon number 2, I've got a 1 carbon group, so that's a 2 methyl. On the green one, a bit boring. Both of those are 1 carbon groups, so that I would have a 3 methyl and a 5 methyl. Now, yeah, we'll wait for a minute, and I don't want to ruin the suspense. And this one, I've got 4 ethyl, 2 methyl, 5 methyl. At this point, if you want to call that 2 methyl, 4 ethyl, 5 methyl, that's fine. I'm kind of lining things up in alphabetical order because I know that's coming. If I have a priority group, nothing has been a priority group yet, but we know that other functional groups exist, so we want to at least introduce the idea now. If there is a priority group is a group that makes the whole thing a different functional group. So here, the orange chlorine changes it. It's no longer an alkane, that is an alkyl halide. So the thing that makes it a more important group, the thing that makes it a new functional group, is going to be a priority group. That has to have the lowest number. So this would be true if you had an alkyl halide. I might as well give you the groups now. That can be fluoro, chloro, bromo, and iodo. So here I've got a chloro group. If there's and that would be true, other priority groups are things that make it an alkene or an alcohol or so on. That thing has to have the lowest possible number. So on this one, I would have to number it from the right to give chlorine the lowest number. It doesn't matter how much stuff is on the other end, I have to give it the lowest possible number. I have to give the lowest possible number to chlorine. Okay? So that's one where if you're just glancing and looking to see which end has more stuff, you might miss it, particularly chlorine, because that Cl can look suspiciously like a CH when it's not a bright orange. Okay? 5, 6, and 7, those rules, we're going to lump them together. So you're going to have number, dash, word, number, comma, number, and then I can put similar groups together with a prefix. What in the world does that mean? I know some of you are kind of frustrated at that because you don't know what it means. I'm getting there. So If I've got multiple groups and I'm trying to put them all into one name, so 3-ethyl-2-methyl, okay, number dash word. If I've got similar groups and I'm putting them on different carbons, but I'm going to lump them together, so 3, 5, then I can put them together with a prefix, dimethyl. Now you might be thinking, wait a second, if I've got 3 and 5, obviously there's 2, why would I also have to say dimethyl to say 2? Good question. I don't have a good answer. We have to do it. Everything gets a name and a number. We got to list the numbers individually, even if it's the same one. 2,2-dimethyl, 2,2-dimethyl. If I take it and put it all together, we'll do this one together, and then I'll give you a second to try it out on your own. I know which direction I'm going to number it from. I know what my groups are. I know where my groups are. So I'm going to put it all together. 3-ethyl-2-methylhexane. Okay? Try this one. Okay? Ones we've already seen before. We've already identified the groups. But here we go. 3,3-dimethyl-octane. Longest continuous carbon chain, followed by this one. Again, pause it if you like, and then come back in a second. Okay? But you should have 4-ethyl, remember the alphabetical order, 4-ethyl-2,5-dimethylheptane. We're going to do a whole lot more. We're also going to add new functional groups and so on. And you'll find that what we're doing is taking versions of this and saying, what does it mean for an alkene? What does it mean for this? What does it mean if we have that? But we're always going to have the same basic rules. Biggest structure, branches, position, where are they, what are they? Anyway, we'll talk to you another time.